So the other way to go about this is doing something which is called p-values opposed to looking at critical regions. So a p-value is the probability, assuming that the null hypothesis is true, of observing a value for the test statistic that is at least as extreme as a value actually observed. So, like this sounds a little weird. So like I said, we're assuming that the null hypothesis is true. So our p-value is the probability of observing a value for our test statistic that is basically like the probability is in comparison to what the null hypothesis says. And we're trying to see how extreme is it. Is it in that 5% region, our alpha level? Is it more probable? Is it a 20% chance that I would get that kind of sample? So the smaller the p-value, the stronger the evidence is against your null hypothesis. Unlike the critical value, the p-value tells us exactly how unusual the test statistic is. So the other case is, we're looking at a region, say there's 5% in the tail. We're just saying we're in that tail, but we don't know how likely it is to get that particular sample mean. P-values will tell you exactly how likely it is. So for many reasons, p-values are often more used in practice, especially when technology is used to conduct a hypothesis test. Typically, when you use any kind of technology, it's going to run it through a p-test. So an online coaching program, like we mentioned before, is supposed to increase your SAT scores. And this one teacher thinks his scores are, oh wait, not the same thing. An online teaching program is supposed to increase SAT scores to greater than 130. So we have that one teacher who said his program was increasing it. So our null hypothesis, once again, was that, well, it's not making a difference. We're still getting means of 530 like we do for all SAT prep programs. Or there's an alternative hypothesis, which is his program is working and they're actually scoring higher than the average. So once again, we assume that we have a sample size of 100. Students are randomly chosen to participate in this program, and their mean score, once again, is 562. The population standard deviation, once again, we know that to be 116. So does this provide strong evidence against the null hypothesis? Well, that's kind of what we want to figure out here. So we figured out the test statistic for this already, and we're still going to use a test statistic. So we still need to figure out what is that z-score. So that z-score we had a mean of 562. The hypothesis test is said it should be 530. We know the samples have a standard deviation of 116, and my sample size was 100. So when we did this last time, we got 2.76. So we're still going to be looking at that score. And we know that it's way up here somewhere. That's what we had figured out. What we want to know is, what is the actual probability that I would randomly get a sample mean of 562? So the smaller the p-value, the stronger the evidence is against the null hypothesis. Therefore, to make a decision to reject the null hypothesis, when using the p-value method, we first have to, or these are the things we have to do, is we have to choose a significance level between 0 and 1. And usually it's going to be somewhere between 0.1 and 0.001, usually somewhere in that range. And let me put that in the correct order. Like I said, usually it's this range. We like to compute a p-value, which is what we're going to get to here in a second. And then if our p-value is less than alpha, then we reject the null hypothesis, because we're saying that this, whatever's going on, is significantly improbable. If your p-value is greater than alpha, then it's a much more likely event to occur. So we do not reject the null hypothesis. So if P is less than or equal A, we say that the null hypothesis is rejected at a alpha level or that the result is statistically significant at the alpha level. So it's still statistically significant. So suppose that the p-value of a hypothesis test is 0.0122. How do we reject the null hypothesis at a level of, or do we reject the null hypothesis at a level of 0.05? So my p-value is 0.0122, and this is less than my alpha level, which is 0.05. So P is less than alpha. If P is less than alpha, we reject the null hypothesis. Is the result significantly significant at alpha of 0.01? So my p-value is 0.0122. This is actually greater than alpha if alpha is at 0.01. This is just a little bit taller, or a little bit larger. So my p is greater than alpha in this case. So here we fail to reject the null hypothesis. So if Ella and Brenna each plan to perform a hypothesis test using the same sample, Ella will use a significance level of 5%. Sorry, stuff got a little crooked here, 5%. And Brenna wants to require a stronger, wants to require evidence to be stronger to reject the null hypothesis. Should she use a significance level that is greater than or less than Ellie's? So like I said, you're thinking about, here we go, that is 5%. So anything in this region is acceptable. So if we want to make this test stronger, we need to have less of an area for it to fill into. So it would have to be less than Ellie's. If Ellie and Brenna each plan to perform a hypothesis test using the same sample, Ellie will use a significance level of 1%, 0.01, and Brenna will use a significance level of 5%, 0.05. Which of them requires the evidence to be stronger in order to reject the null hypothesis? So once again, it goes back to thinking about those tails, right? So if we're looking for evidence, let's say this is 5%. Well, 1% would have to be a smaller area to look at. So we're saying, can the p-value be in this area, or the p-value going to be kind of in this area? So this has a smaller area. That is a stronger test. So Ellie, in this case, is requiring stronger evidence. So the mean height of adult men in the US is 69.7 inches with a standard deviation of 3 inches. A sociologist believes that men may be taller, a sociologist believes that taller men may be more likely to be promoted, so the mean height of male executives would be greater than the mean of the entire population. So we're looking at this. Null hypothesis, well, alternative hypothesis, they're claiming, I keep using the old symbol, they're claiming that if they look at executives, they should be taller than the average. So the null hypothesis is, well, they're wrong. They're still going to be the same as what is average. Taller men are not more likely to be promoted. A simple random sample of 100 male executives has a mean height of 69.9 inches, which is taller. We assume that the standard deviation of male executives is going to be 3. That's about what it roughly is for the population of all men as well. We can conclude that male executives are taller on the average than the general, or can we conclude that male executives are taller on the average than the general male population at a alpha of 5%? So we need to first find a test statistic. And as always, it's always going to be a test statistic of the mean, our sample mean. So our sample mean is 69.9. The mean from our population or from our hypothesis test is 69.7. The standard deviation for male executives and height is 3 inches, and my sample size is 100. So my test statistic that's my spot, my calculator. That is going to be 0.02 or 0.2, I'm sorry, divided by 3, which is divided by the square root of 100. And that is going to be 0.66. We'll do 67. Yeah, I had something wrong with my calculation there. All right, so what we need to figure out is that we are still looking at really like a left tail test. So we want to know if 69.9 inches are here and the average is 69.7, how improbable or probable is this example here? So we need to figure out this area. So we want to figure out what is the probability that I would collect a sample of men and their height would be, because I'm looking at that right tail, would be larger than 69.7 inches. Or once again, what is the probability that my z-score, my test statistic, would be greater than 0.67? So this requires us to go back and either use the z-tables or we can use the TI-84 to find this. So just to remind you, the TI-84, if we go to second bars, that takes me to distributions, and we want to have the second one here. So what we are looking for, like I said, we're looking at those male executives. So 69.7 is the average. We have a sample where it is 69.9. So we're trying to figure out this area here. What is the probability that we would find men who are 69.9 or taller? So we're looking for the probability that a sample mean of men who are executives would, or sample mean of just men would be greater than 69.9 inches, which we said was converted to a z-score of being greater than 0.67. So we're trying to find this area here. So the lower bound on that area, if we're doing this with z-scores, is 0.67. The upper bound, as far as z-scores go, so we just pretend this keeps going forever and ever. I do like 100. So we just need that probability. So we can leave the rest alone because if we're talking about it in z-scores, this is what I'm looking at. And the probability of this event is going to be 0.25. So I was just looking at this from the viewpoint of just z-scores. So just looking at that region. All right, so what this means is that this sample is highly probable. So what we had found was that our P level, so our P level was that probability that I would have a sample of men and that their height would be 69.9 inches or greater. Like I said, we did this with a z-score, but we ended up finding that that probability is 0.25. So my P, alpha is 5%. My P is greater than alpha, so we fail to reject the null hypothesis. So remember, my null hypothesis was that I take executives and their mean height would be 69.7 inches. My alternative hypothesis was that only tall men get to be executives, so we expect it to be greater than 69.7. And I just said, I fail to reject this claim. I don't have evidence of the other one. We do not have evidence that taller men are more likely to be promoted. Okay, so I can't really say that, oh yeah, that taller men or that all men have the same likelihood of being promoted, which is what this is claiming here. I just can say that I don't have evidence against it. I have evidence, however, that I don't really have any evidence to support that taller men are more likely to be promoted.